Hello, welcome to the course on Hadoop development offered by Data Raj Academy. My name is Venu and in today's session we will discuss about some of the technologies used for handling big data. I hope you will all find this session interesting and informative. In today's session we will discuss about scalability in computing world. We will explore various models of scalability. We will see how Moore's law has suited us for the past few decades. Then we move on to understand the need for distributed and parallel computing. What are the factors that have favored this computing pattern? Finally, we will try to understand on a high level what Hadoop offers, how it has come to the rescue to the programmers in handling big data using distributed environment. So let's get started. Let us start by understanding what is a big data technology. In the simplest terms, any technology that enables you to handle huge volumes of data is a big data technology. Now, what do we mean by handling? It means a big data technology enables you to store big data, that is huge volumes of data, and also enables you to process it after storage. That is, there are two aspects of handling. One is storage of big data and the other is processing this stored big data. Hadoop is one of the big data technology. Hadoop allows us to store huge data in its file system called Hadoop distributed file system and also allows us to process that data with MapReduce. MongoDB, for example, is also a big data technology. It allows big data to be stored in its database. It also provides a querying language to query that stored data. There are many other big data technologies in use today other than Hadoop, like Apache Spark and NoSQL databases like HBase, MongoDB, Cassandra, etc. What is scalability in computing world? Let us take an oversimplified case to get started. I have a laptop which has 2 terabytes hard disk, 2 gigabytes RAM, and 2 cores processor. The extent of its usability or its applicability is limited by its configuration. That is, I can use only those softwares or I can only do those tasks whose minimum system requirement is met by the configuration of my laptop. Now, a friend of mine visits me with his external hard disk of 3 terabytes full of data, which comprises of variety of files. There are text files, images, audio, and video files. He wants me to store all the data in my laptop. But in my laptop, out of 2 terabytes, there is only 1 terabyte free space available. What options do I have? Option 1. I should buy an external hard disk with at least 2 terabytes and plug it into my system. Once I do that, I have full 3 terabytes free space available now, and I can copy the data. Or I should replace my old hard disk of 2 terabytes capacity with a new hard disk of at least 4 terabytes capacity. By resorting to either of these two techniques, I can meet my requirement. Now, what I have done is, I have scaled up my system's configuration from 2 terabytes to 4 terabytes. Let us note the term scaling up. Scaling is a transformation that enlarges or diminishes a system. Scaling up is a process of either adding something to the existing configuration or replacing the old with a new one. Scaling down is just the opposite of scaling up. This scaling up and scaling down can also be called as vertical scaling. In our case of vertical scaling, we have enlarged our system by replacing an old hard disk of 2 terabytes with 4 terabytes. But if we were to replace the new hard disk of 4 terabytes with old hard disk of 2 terabytes, we are said to be diminishing our system. A system or a process whose performance improves after adding hardware proportionally to the capacity added is said to be a scalable system. We can certainly upgrade or scale up our hardware to improve performance. But depending on the hardware platform, there is a limitation on the number of processors, system memory, or number of disks that can be added to the same single server. To understand this, let us slightly complicate our case. What if the volume of the data to be copied is 300 terabytes instead of 3 terabytes? Should we still resort to vertical scaling? As the volume of data grow, we have an option to scale up our storage and computing capacity, which we did. But if the volume of data continues to grow with an incredible speed, scaling up hardware limitlessly is neither feasible nor advisable. In the scale-up model, faster and higher capacity hardware is added to a single server, but this scale-up approach has a limit after a point of time. It is also cost ineffective given the need for expensive, faster and higher capacity hardware components. Very high cost of software licenses required to run on such high-end servers. Maintenance cost of these high-end servers is also very high. Since this approach relies on a single high-end server, backup and recovery strategy should be in place, which also turns out to be very expensive. Because in case of failure of such single high-end server and with a lack of any backup strategy, it could lead to an organizational disaster. Alternatively, at a point where vertical scaling or scaling up is no more feasible, to handle the huge volume of variety of data coming at incredible speed, we can opt for horizontal scaling. To scale horizontally, that is to scale out or to scale in, means to add more nodes to or remove nodes from a system, such as adding a new computer to a cluster of machines. That is, instead of opting for a high-end monolithic single server, we can connect multiple computers together to form a computer cluster. The aggregated or combined storage space and computing power of this configured computer cluster often far exceeds that of a high-end single server. Let us try to understand horizontal scaling model by taking another oversimplified case. An online retail company, ByteCart, is keen on performing data analytics on data derived from free external data sources to improve their company's analytics and decision-making system. The volume of data available from external data sources is very huge, and for all the aforementioned reasons, ByteCart decided to go for horizontal scaling model. They have realized that investing on a single machine with 4 times the power of a standard PC costs a lot more than putting 4 such PCs in a cluster. Clusters are usually deployed to improve performance and availability over that of a single high-end expensive server. Clusters are also typically more cost-effective than single computers of comparable speed and availability. Cluster computing is based on a connection of multiple servers in a network. This network is known as a cluster, in which the servers share the workload among them. A cluster can be either homogeneous, which comprises the same type of commodity hardware, or heterogeneous, which consists of different types of hardware. ByteCart has set up an in-house cluster comprising of 3 identical nodes, with each node having 5 terabytes disk space. In this case, ByteCart has scaled out the system from 1 computer to 3 computers. Let us note the term scaling out. Scaling out is a process of adding more nodes or computers to the existing ones and interconnecting them together. Scaling in is exactly the opposite of scaling out. This scaling out or scaling in can also be called as horizontal scaling. A smaller cluster with smaller number of nodes can be easily scaled out to form a bigger cluster based on our requirement. Let us look at some of the factors that favor horizontal scalability. Computer clusters emerged as a result of convergence of a number of computing trends, including the availability of low-cost, high-performance microprocessors and drop in computer prices. High-performance computing applications such as seismic analysis and biotechnology workloads have adopted low-cost commodity systems for tasks that once would have required supercomputers. And also the availability of software for high-performance distributed computing. The development of high-speed interconnects such as gigabit Ethernet, InfiniBand, and MyriNet further fueled this model. It proved cost efficient to obtain the desired level of performance by using a cluster of several low-end computers in comparison with a single high-end computer. A distributed system can provide more reliability than a non-distributed system, as there is no high risk of failure. Moreover, a distributed system may be easier to expand and manage than a monolithic uniprocessor system. Let us have a look at the cluster configuration. It is a 3 nodes cluster. All the 3 nodes are identical to each other in configuration. That is, in terms of number of processors, memory, and disk space. The nodes of a cluster are connected to each other through fast local area networks, with each node, that is computer used as a server, running its own instance of an operating system. They are connected to each other to form a cluster so that their combined storage space and computational power can be utilized for data intensive and compute intensive workloads. Combined disk space of the cluster is 15 terabytes. This cluster can be called as a distributed system. A distributed system is a network of autonomous computers that communicate with each other in order to achieve a goal. First, we will look at distributed systems. These are interconnected groups of independent computers that need to communicate with each other to get a job done. The computers in a distributed system are independent and do not physically share memory or processors. Bytecard's main purpose for setting up this cluster is to handle big data. As discussed earlier, first aspect of handling is to store the data. When Bytecard wants to store data sets, usually of the size that are too large to fit on a single machine, the data sets need to be broken down into chunks, and these chunks of data are to be distributed across the cluster based on the disk space availability of each node. There are many challenges faced by the programmer in accomplishing this. Tasks like checking for availability for disk space in the cluster. If the space is available, then identifying the nodes on which data can be stored for optimal efficient write-read operation, breaking the data set into number of blocks and distributing those blocks of data across the cluster, remembering the locations of the distributed blocks in the cluster, all have to be taken care by the programmer. Now, what if one of the node goes down or fails during storing, that is, while write operation is in the process or after storage? What if the file system on one of the node gets corrupted? Similarly, when we want to retrieve the whole dataset at some later point of time, a programmer has to handle tasks like identifying the blocks of data scattered across the cluster, streaming them in an order, handling node failures and network latencies, etc. Programmers also have to take care of the coordination between the nodes to provide a service, share data, or even store datasets that are too large to fit on a single machine. When there is a network involved in the architecture, all the possible network related issues may creep into the picture, which have to be handled by the programmer. Second aspect of handling big data is being able to process the stored data efficiently. We know how to design or develop programs for a single system to run. The user program, its runtime environment, and the data which has to be processed by the user program are residing on the same system. Let us see an example to understand this better. A programmer has a small text file numbers.txt in his computer. He wants to process this file to find out the largest number in the text file. So, he developed a Java program largest from textfile.java to accomplish this task. In this case, the data file numbers.txt and the program largest from textfile.java are located in the same computer. When the program is executed, the Java runtime environment JRE, which is installed on the same system, runs this program and yields the output. If we closely look at the program, major part of the program is the actual logic of what the programmer wants to do with the data, whereas the plumbing work like handling exceptions is bare minimum, primarily because we are working on a single system and there is no network involved. So, developing the program to process data in a single system is fairly simple and straightforward. But Programming for a system like distributed network is lot more complex. We will try to understand few terms like distributed network, distributed program, and distributed programming in more detail before we venture further to understand the complexities involved in distributed programming. The word distributed in terms such as distributed system, distributed programming, and distributed algorithm originally referred to computer networks where individual computers were physically distributed within some geographical area. The terms are nowadays used in a much wider sense, even referring to autonomous processes that run on the same physical computer and interact with each other by message passing. That is, multiple virtual machines can be launched on a single physical machine, and these multiple virtual machines are configured to form a cluster. This is a schematic view of a typical distributed system. The system is represented as a network topology in which each node is a computer and each line connecting the nodes is a communication link through which nodes communicate with each other. Distributed computing refers to the use of distributed systems like cluster of autonomous computers to solve computational problems. If we check out the same distributed system in more detail, each computer has its own local physical resources like memory, processors, and disk space, and also they have their own copy of operating system. Information can be exchanged only by passing messages from one node to another by using the available communication links. In distributed computing, a problem is divided into many tasks, each of which is solved by one or more computers, which communicate with each other by message passing. We will understand this better when we discuss the MapReduce concepts. Now, we know what a distributed network is. A distributed system or a network is a collection of independent computers interconnected via a network capable of collaborating on a task. Distributed storage of huge data sets results in breaking down of those huge data sets into smaller blocks and distributed across the cluster of nodes. Distributed programming is the process of writing programs which are capable of running on a distributed system or a network of computers. This program, developed by a programmer, which is meant to run on a distributed system or on a network of computers to process the huge data set that is scattered or distributed across the cluster of nodes, is called a distributed program. A programmer has to consider many factors while developing a distributed program, as it involves a network of computers. It requires coordinating multiple computers or nodes and processors as data is distributed across the nodes. It involves breaking up the given job into smaller tasks, surveying the available resources at hand, and assigning the tasks to the resources that are interconnected in a network. Sometimes, resources develop some technical problems and fail to respond. Such situations should be handled by reallocating the tasks to some other available resources in the cluster. Another important task to be kept in mind while working on a distributed network is load balancing. Load balancing is essential to improve the distribution of workloads across multiple computing resources such as computers or nodes. Load balancing aims to optimize resource use, maximize throughput, minimize response time, and avoid overload of any single resource. Though organizations are convinced that distributed and parallel computing are the way to go to address their big data challenges, handling all these complex issues is a daunting task to a programmer, which could discourage organizations from adopting this approach. So, what is the way out? How do we reap the benefits of a distributed system whilst making it easy for programming? If we keenly observe, most of the complexity in distributed computing is involved in handling issues related to the network. That is, if a programmer develops a distributed program, major chunk of the code is written to handle the cluster components related issues, while the code implementing the actual business logic is just a few lines. Since most of the cluster components related issues are common, what it would be like if there is some kind of cluster middleware, a software layer that sits atop the nodes and takes care of all the challenges of distributed computing discussed earlier. All the activities of the computing nodes are orchestrated and coordinated by this clustering middleware software, and it allows the users or clients to treat the cluster as by and large one cohesive computing unit. Example, via a single system image concept. In this single system image concept, the programmer's primary focus is on the business logic which deals with how to process the data, rather than on the cluster resources management and network related issues. All that the programmer has to do is write the program containing the business logic in accordance with few rules and guidelines established by cluster middleware software. On submitting this program, the cluster middleware software allocates resources and runs the program on the allocated nodes and yields the output. From a programmer's perspective, the cluster middleware software appears and acts like some kind of operating system of the cluster as a whole. So, the life of programmer just got simpler. Hadoop is one such popular cluster middleware software. Hadoop is a framework or a software library that allows its users to store huge sets of data across distributed clusters of computers, and also allows to process those large distributed datasets. When Hadoop is installed on a cluster, Hadoop related daemons or background processes run on every node of a cluster. Every Hadoop process running on a node keeps track of the details of the node on which it is running, and there is some kind of communication and coordination between them. Hadoop framework in this way keeps track of the health of the cluster. That is, it identifies if there are any node failures or any other network related issues. Hadoop framework takes care of coordination between the nodes and also provides for synchronization and communication between them. Now, let us see how Hadoop software helps in handling big data. In simple terms, when a client wants to store a dataset in the cluster, Hadoop framework takes care of the following tasks. Hadoop surveys or checks for availability of nodes and allocates the active nodes in the cluster to store the dataset. Allocation of the nodes is not done randomly but follows an elaborate efficient algorithm. Dataset is broken down into smaller pieces or blocks of data to be distributed across the cluster to be stored in the allocated nodes. Hadoop also provides a fault-tolerant mechanism. That is, Hadoop stores multiple replicas of the blocks of data of the dataset so that even in the case of failure of few nodes, complete dataset can be extracted when in need. Hadoop remembers the block locations of the dataset so that it can use that metadata to extract the complete dataset in need. Hadoop provides for a high availability mechanism by maintaining multiple replicas of the blocks. These replicas are stored at varied locations so that in case of any node failure, particular data block of a file can be extracted from some other active node. So, Hadoop software runs on a cluster of commodity machines and provides the features like fault tolerance and high availability by maintaining replicas of blocks. We will discuss more on these in detail later. Hadoop is a scalable system. The term scalability is a generic term which can be used for both hardware and software. If the performance of a software running on a system increases on upgrading the system hardware, the software is said to be scalable. Hadoop is a software which generally runs on a cluster of machines. If more number of machines are added to the cluster, the performance of Hadoop improves. Hence, Hadoop software is a highly scalable system. Now, let us see how Hadoop provides for distributed processing of this distributed data. Hadoop is designed by adopting move code to data approach, which makes sense for the data intensive processing. The programs or code to run are orders of magnitude smaller than the data and are easier to move around. Also, it takes more time to move data across a network than to apply the computation to it. So, let the data remain where it is and move the executable code to its hosting machine. Hadoop also provides for fault tolerance while processing. That is, if a process is running on a data block residing on a node, and if the node fails for some reason, the process will be reallocated to some other active node, thus taking care of the failures. It is very easy to create programs with Hadoop using the MapReduce framework. What is equally important is what you didn't have to do, like worrying about partitioning the data, determining which nodes will perform which tasks, or handling communication between nodes. Hadoop handles this for you, leaving you free to focus on what's most important to you, your data, and what you want to do with it. Hadoop is a distributed framework or software library or a set of processes that run on all the nodes of the cluster to make the cluster manageable. In the next session, we will explore Hadoop framework in more detail. We will see some of the compelling features of Hadoop framework which led to its widespread adoption by many organizations as part of their big data solution. Finally, we want to hear from you. As the viewer of this tutorial, you are our most important critic and commentator. We value your opinion and want to know what we are doing right, what we could do better, and any other words of wisdom you are willing to pass our way. We welcome your comments. Your feedback will be enormously helpful in improvising the final shape of this course. So please subscribe to the DataRaj channel and contribute any questions, comments, or suggestions in the comment section below. Thank you.